Hi viewers, in this lecture we'll discuss about the concept of electric field and electric lines of force. So as we have discussed in our previous lectures that whether a charged particle is at rest or it is in motion, it always produces an electric field around it. So what is the meaning of this electric field? You must have heard in your biology lectures that the dogs, they mark their area or they mark their field by urinating around the area, so that when another dog enters into the area, it can smell the pheromones secreted by the dog in its urine and it will not venture to enter into the area of another dog. Similarly, the charges, they exert forces on each other. We know that like charges repel and unlike charges attract. So when attracting and repelling, the charges, they exert electrostatic forces on each other. And we know that the electrostatic force is one example of an uncontact force. So that means when one charge is attracting or repelling another charge, it must be doing it from a certain distance. That means one charge can attract another charge or repel another charge without being in actual contact with the charge. See, suppose we have a positive charge, then this positive charge can attract another negative charge, and it can also attract the negative charge without being in contact with the negative charge. The force between the positive and negative charge is electrostatic, and the electrostatic force is one example of an uncontact force. So this positive charge will attract this negative charge without being in contact with the negative charge. Now another thing is that this charge, this positive charge, will attract the negative charge within a certain range only. It will not attract the negative charge if this negative charge is at infinity. Suppose this negative charge is situated at this distance. Suppose this distance is several kilometers. Now this positive charge cannot put force on this negative charge. It cannot put an attractive force on this negative charge. That means it cannot attract the negative charge at this distance. Now if we bring the negative charge closer, then you will see that at a certain distance the negative charge will be attracted by the positive charge, and before that it will not attract the negative charge. So there is a certain range beyond which this positive charge cannot attract the negative charge. That means beyond a certain distance this charge will not be able to put force on another charge. Suppose this positive charge will start attracting the negative charge at this distance. Then if you will take this distance as radius and you draw an imaginary sphere, then the total space lying inside the sphere will be called as the electric field of this charge. So if you take the radius as distance as the radius and you draw the imaginary sphere, then the entire space falling within this sphere will be called as the electric field of this charge. So what is the literal meaning of this field? That means within this sphere only, this charged particle can put force on another charged particle. You see, if a negative charge will be lying outside this sphere, it will not be attracted by the positive charge. But once it will enter into the sphere at anywhere, at any point, within this space, any charged particle can feel the force due to this positive charge. But outside the sphere, no charged particle will experience any force due to this charge. So this region of space surrounding this charged particle will be called as the electric field of this charged particle. So the electric field of any charged particle refers to the modified space surrounding the charged particle within which its influence can be realized. That means within the sphere within which it can attract or repel another charge, or it can exert force on another charge, that region of space is called as the electric field of that charge. Now this charge is called as the source charge because this produces the electric field. So the charge due to which the electric field is produced is generally called as the source charge. That means this field belongs to the charge, this charge. So this is the concept of electric field. Now in order to represent the electric field, because you cannot see the field but you can experience its effect. You see, if you are having a charge at a particular point, then you cannot see the field around it, but you can experience the effect of the field. How? Once you bring another charge into the field or inside the field, then it will be either attracted or repelled by the source charge depending upon the nature of the charge. But outside the field, it will not experience any type of force. So that effect is real, but the field is abstract because you cannot see the electric field around a charge. Now as the electric field is abstract, in order to represent it or in order to study the effect of the electric field, we generally take the help of three parameters. One is your electric field intensity, and your second is your electric lines of force, and lastly electric potential. So we study the electric field with the help of these three parameters, and this is the vector representation of the electric field. This is the geometric, or you can say the diagrammatic representation. Geometric or diagrammatic representation of the electric field, and this the electric potential is the scalar representation of the electric field. So we take the help of these three parameters in order to study the electric field. Now coming to the first one, the electric field intensity. Generally the strength of this is also called as, otherwise called as, the electric field strength. Or the strength of electric field. Now what is this term mean? What does this term mean? You see, if you have a charged particle, if you have any charged particle Q, then this charged particle will give rise to an electric field around it. Now if you have another charged particle, if you bring another charged particle into the field of this charge, then that charge will experience a force inside the field of this charged particle. It is quite evident from the definition of electric field. Suppose you take a unit positive charge. We generally represent it by Q naught. So remember, a unit positive charge is otherwise called as a test charge. A test charge is generally called as, represented by Q naught, is generally called as a unit positive charge. So if you will consider, or you will take a unit positive charge inside the electric field of this charge, then this charge will experience a certain force, certain amount of force. So that amount of force, the magnitude or the strength of that force experienced per or experienced by this unit positive charge is called as the electric field intensity or the electric field strength. So the electric field intensity, it refers to, or it is calculated at any point inside an electric field, because outside the field there is no meaning of electric field. The field will be zero, so the field strength will be also zero. So the electric field intensity or the electric field strength is calculated at any point inside the electric field. So the definition will be the electric field intensity at any point inside an electric field is the amount of force experienced per unit positive charge or a test charge placed at that point. That means if I want to calculate the electric field intensity at this point A inside this electric field, then what I have to do, I will place a test charge, otherwise called as a unit positive charge. That means the charge must be having a positive sign and its magnitude should be very, very small. That means 1 unit. We are generally taking it as a unit positive charge. The sole aim of taking a unit positive charge is that if we take a very small charge, then the field produced by this test charge will be pretty small and it will not interfere in the calculation. That means here we will only calculate the strength of the field of the source charge. But if you will take a very small amount of charge here, then the field produced by this smaller charge will be very small and it will not interfere in the calculation. So that is why we are taking a very small amount of charge having a positive charge. That is why we are taking it as a unit positive charge, and this is the field of the source charge. So in order to not interfere the field of the source charge, we are taking a very small unit positive charge. So the electric field intensity at any point inside an electric field is the amount of force. So electric field intensity is equal to the amount of force experienced per unit positive charge or a test charge placed at that point. So E is equal to F by Q naught, where Q naught is called as a test charge whose magnitude is very, very small, or 1 unit. We generally take it as 1 unit and its sign is positive. And the direction of this electric field, as electric field is a vector quantity, so this is a vector quantity. Remember, electric field is a vector quantity and its magnitude is given by F by Q naught and its direction. So as it is a vector quantity, it must be having a direction. So the direction of electric field intensity will be along the direction of the force, because in this formula the force is the vector quantity and charge is a scalar quantity. So the direction of the electric field intensity will be decided along the direction of the force. So definitely, as we are placing a test charge, you see the test charge is always positive. We have taken it as the test charge is always positive, then the direction of the force will depend upon the sign of the source charge. You see, if the source charge will be positive, then the direction of this electric field intensity will be away from the charge. If this is positive and test charge is always positive, so the direction will be always away from the charge, away from the source charge. And if the source charge is negative, then the direction will be towards the charge. So the direction of electric field intensity will be along the direction of the force between the charges. Now coming to the unit and dimension of electric field intensity. You will see that E is equal to F by Q or F by Q naught. So its unit will be equal to, in SI system it will be, force will be in Newton divided by charge will be in Coulomb. So 1 unit will be Newton per Coulomb. And we can also write it as, in place of, in both the numerator and denominator, we can multiply it by displacement. So F into S by Q into S. So it will be work divided by Q into S. So that will give us, if we put the units here, so the SI unit of work is Joule divided by Coulomb into meter. So this is also another unit, remember. But we also know that later we will study that the joule per coulomb is volt, because you will see the V, the potential is equal to work done per charge. So V is equal to W by Q. So here it is already there. So here it is V is equal to W by Q, means it will be joule per coulomb is equal to V, means volt. The SI unit of V or potential difference is volt. So volt will be joule per coulomb. So here it is already joule per coulomb is there. So it will be equal to volt per meter. So this is also another unit of the electric field intensity. Generally multiple choice questions are asked to find out which of the following unit of the electric field intensity is not correct. So remember, these are all the derived units of the electric field intensity. Now proceeding to the dimension of the electric field intensity, you will see that so the E will be equal to F by Q. So that will give us, in place of F it will be MA, so MS by T square, so it will be M1 L1 T minus 2 divided by the dimension of Q will be, so Q is equal to IT, so I is the current and T is the time, so it will be ampere 1 and time 1. So on solving it will give us M1 L1 T minus 3 ampere minus 1. So this is the dimensional formula of the electric field intensity. So generally the electric field is represented in terms of electric field intensity or the strength of electric field, because by only saying the electric field it does not carry any meaning. So generally the electric field is represented in terms of the electric field intensity or the electric field strength. Now coming to the next thing, that is the electric lines of force, a very important concept, that is the electric lines of force. Now see, the concept of electric lines of force was introduced by Sir Michael Faraday, and he used in order to represent diagrammatically or geometrically the direction or the alignment of the electric field around charged particles. So the definition of electric lines of force is, so these are either straight or curved lines which are used to represent the electric field. So the first definition will be definitely, so these are either straight or curved lines which are used to represent the electric field. And the secondly we can say, which is the more appropriate definition, you say, so any line, if these are imaginary lines, so if any line, we can only call it as a lines of force if a tangent drawn at any point to the lines of force represent the direction of electric field intensity at that point. So any line will be called as, any imaginary line can be called as a lines of force only if a tangent drawn to the lines of force at any point gives the direction of electric field intensity at that point. So electric lines of force are either straight or curved lines such that a tangent drawn at any point to the lines of force represent the direction of electric field at that point. Now another definition can be quoted for the lines of force is that it is the path followed by a test charge. As we have already discussed, a test charge is a unit positive charge. So it is the path followed by a test charge or a unit positive charge placed in an electric field when it is free to do so. That means if you want to draw the lines of force in an electric field of an electric field, then what you do? You simply take a unit positive charge, you just release it in the electric field and see in which direction it is moving. So the path followed by that unit positive charge will give us the lines of force. So reversely you can also say it is the path followed by a unit positive charge placed in an electric field when it is free to do so. That means it must be doing so freely. We will not apply any external force. We will simply release the unit positive charge in the electric field, and we will see that when it is free to do so, that means when it is free to do or free to move, then in the direction or the path in which it will move, that will give us the electric lines of force. So these were the definition of electric lines of force. So it is just a tool. Electric lines of force is just a tool to represent the electric field, the abstract electric field, because as we cannot see the electric field, so in order to represent or study the electric field, in order to visualize, we are taking the help of the electric lines of force. Now coming to the properties of the lines of force, this is a very important concept also. Properties of lines of force. So the first, definitely the lines of force are the lines which represent the electric field. So the first property is they can be straight or curved. The lines of force, they can be straight lines or they can be curved lines also. They can be straight or they can be curved. And the second property is the tangent drawn to any lines of force at any point gives the direction of electric field intensity at that point. Now the third property is two lines of force will never intersect each other. You see, so the two lines of force will never intersect each other. Because, so let us explain it, because this question is quite frequently asked in various board exams. Because the reason for this is, suppose these are two lines of forces, if they cross at a point, if they intersect at this point O, then we can draw two tangents to the two lines of force at the same point. From this point I can draw a tangent to these lines of force. I can also draw a tangent to these lines of force. So at this point we can, as we know, the tangent represents the direction of electric field intensity at any point. So at the same point we will get the two direction of electric field intensities, but which is impossible because electric field intensity is a vector quantity and at a particular point it will only have one direction. But if two lines of force will intersect at one point, then at that point two tangents could be drawn to the two lines of force which will represent the two direction of electric field intensity at the same point, which is impossible. So two electric lines of force will never intersect each other. Now coming to the fourth point, the electric lines of force, they start from the surface of a positive charge and end on the surface of a negative charge. So they start from the surface of a positive charge and end on the surface of negative charge. You see, if we have a positive charge and a negative charge, suppose these are point charges, then the electric lines of force, it will always start from the surface of a positive charge and end on the surface of a negative charge. Now this is also quite evident, because if you want to draw the electric lines of force, what we will do, you just take a positive charge. As per the concept, you take a unit positive charge and you release in the field of this charge and see in which direction or in which path the positive charge is moving. So that path will be the lines of force. So here if we release a unit positive charge or a test charge, then the test charge is positive, so that will be repelled by this positive charge and that will be attracted by the negative charge. So it will definitely move from the positive to negative charge, and that path will give us the lines of force. So in case of a positive and negative charge, the lines of force, they always start from the surface of a positive charge and they end on the surface of a negative charge. So if, let us draw it elaborately, suppose this is a positive charge and this is a negative charge, you will see that the electric lines of force, they start from the surface of a positive charge and end on the surface of a negative charge. So they are ending on a negative charge and they are starting from a positive charge. So this is the diagram which is representing the lines of force are starting from the surface of a positive charge and ending on the surface of a negative charge. Now from this diagram you can also see that the lines of force are discontinuous curves. This is also very important thing. You can see that the lines of force are discontinuous because they are starting from the surface of a positive charge and ending on the surface of a negative charge. They are not passing through the charge or through a charged body or through a conductor. You will also study it later on that the lines of force, they will never pass through a conductor or they will never exist inside a conductor. That is why the electric field inside a conductor is zero. So as the lines of force are not passing through a charged body or through a charge, so they are not forming closed loops. They are not forming closed loops and they are not continuous curves, they are discontinuous curves. The electric lines of force, they are discontinuous curves. So the fifth point is they form discontinuous curves. Or you can say they do not form closed loops. Now the next point is, now the lines of force, they are starting and ending on the surface of a charged body or surface of charges perpendicularly. That means when they are starting from the surface of a positive charge, they are starting normally, and when they are ending on the surface of a negative charge, they are also ending normally. So that means the angle between the electric lines of force and the surface of a conductor will be always 90 degree. This is also very important point. Or you can say here the angle between the lines of force and the charged body is always 90 degree. So the lines of force are always perpendicular to the surface from which they are emerging or the surface on which they are ending. So they start and end normally. So here this each angle must be perpendicular, must be 90 degree. So the electric lines of force are always perpendicular to the charged body or always perpendicular to the surface of the conductors. Now the next point is, suppose for an isolated conductor, so the 7th point is, if we have an isolated charge means separate charge. So it can be a positive charge or it can be a negative charge. So how to draw the lines of force? Again the concept will apply. We'll take a unit positive charge and we'll place in the field. So here the source charge is an isolated positive charge. Now in order to draw the lines of force, you just take a test charge, that is a unit positive charge, and place in the field of this source charge and see in which direction it is moving. So if you will take a source test charge, then the test charge will be positive. So if you release it in the field, it will move away from this charge. So it will move radially away. So the direction of lines of force from an isolated positive charge will be radially outwards. So for isolated positive charge, the lines of force are straight. They are straight lines. That means you can say that if it is from this point, we saw that the lines of force, they start from the surface of a positive charge and end on the surface of a negative charge. Now here it is starting from the surface of a positive charge but ending at infinity because there is no negative charge. And here you can say that here also if you will put a positive charge, unit positive charge, then it will be attracted, so the direction will be radially inverse. Here also you can say that the lines of force are beginning or originating at infinity and they are ending at the negative charge, on the surface of this negative charge. So here it is straight, the lines of forces are straight, they are radially outwards, direction is radially outwards. And another thing is its symmetry. You see, if you see all the lines of force emerging out from this positive charge, if you imagine it in around this positive charge in a region of space, then you will see that all the lines of force, if you will join them, you can see them as a sphere. So if you see all the lines of force emerging out from this positive charge, it will look like a sphere to you. So the symmetry will be spherical. So for an isolated charged body, the lines of force have spherical symmetry. The same case is here. Here only the lines of force are again straight lines, but it is radially inverse because the direction is according to the direction of movement of a unit positive charge or the test charge. As it is negative, so it will be attractive, so it is radially inverse. And again it is having spherical symmetry. So in exam the question are asked like this, that what is the nature of lines of force, electric lines of force for isolated positive charge. So these are straight lines and these are radially outwards. The lines of force will be directed radially outwards and forming a spherical symmetry. Now the next point is, your number 8 point will be for a positive and a negative charge. I have already drawn it. So this is for isolated charges, and if we have two equal and opposite point charges, suppose this is positive and this is a negative point charge, so the lines of force will start from positive and end at negative. So this will look like this. So from positive the direction will be outwards, and for negative the direction will be inverse. So you can see that the lines of force are starting from positive charge and ending at negative charge. If in this case we told that the lines of force will form a spherical symmetry, then in this case what will happen? If you able to visualize it, then you will see that they will start normally and end normally. So if you collect, or if you collectively see all the lines of force, then you can visualize it as a cylinder, because here in all region of space the lines of force will arrange like this, will be arranged like this. So if you will collectively see them, then you can see that this is forming a cylinder. So this will be forming a cylinder. That is why in case of two dipole, we'll study it later on, that we call it as a dipole. That means two equal and opposite point charges. So this, in case of a two equal and opposite point charges, the lines of force will form a cylindrical symmetry. So the symmetry will be cylindrical. And another thing is that it is also one characteristics of lines of force, that in case of opposite charges, in case of positive and negative charge, so this is a positive negative charge, what will happen, as the positive and negative charge will attract each other, so they will move closer, the positive and negative charges, they will move closer, so the lines of force will contract longitudinally. So they are contracting longitudinally along the length, along the perpendicular axis. They are contracting, they are coming, as the positive and negative charges are coming closer, so the lines of force, they contract longitudinally. So for unlike charges, for opposite charges, or unlike charges, the lines of force contract longitudinally. So the lines of force, they contract longitudinally, which indicates the attraction between unlike charges. Similarly, for like charges, you can see, if we will draw the lines of force for two positive charges, two positive point charges, then you will see that the lines of force, they will exert lateral pressure and they will move away from each other. Always remember the direction. For positive, the lines of force will definitely outwards, so the direction is some like this, and as this is the force between the positive and positive charge is repulsive, so the lines of force are, they are repelling each other and they are exerting lateral pressure on each other. That is why they are becoming like this, like a jellyfish appearance. If you see that, you will see that it is becoming like a jellyfish. So this is exerting lateral pressure. So the lines of force, they exert lateral pressure. This is point number 10. They exert lateral pressure for like charges. Lateral pressure for like charges. So the like lines of force, they exert lateral pressure, which indicates the repulsion between two like charges. Similarly, in case of two negative charges, we can also draw it like this. So if it is negative charge, two negative charges, only the direction will be reversed. So they will repel each other, no doubt, but the direction will be inwards. That means towards the charge. This is quite easy because the direction will be always as per the direction of a motion of a unit positive charge or a test charge. Now another thing is that, as we know, as we have already discussed in our equilibrium of charges, here the same concept will be also applied. You will see that in between, at some point or at the middle point of the line joining these two charges, you will see that the net electric field intensity will be 0, because electric field intensity is a vector quantity. So for like charges, it will lie at a certain point in between these two charges. The net electric field intensity will be 0 and we will get a neutral or null point. This is called as a null point, and there will be no electric lines of force. because the net field will be 0 at that point. Net electric field intensity will be 0 at that point, and that point will be called as a null point. So at null point there will be no lines of force because there will be no field. Now the next point is number 11 point is the distance between the lines of force. They indicate the strength of the field. You see that if at a certain area the lines of forces are closer, then it indicates a stronger field. So the distance between, if the lines of force, if the density of the lines of force is more, that means the lines of force are more dense at a region of space, then that at that point we can say that the field is stronger. And if the lines of forces are farther away from each other, or the distance between the lines of forces is more, then it indicates a weak field. So here the field, this field is greater than this field. So E1 is greater than, suppose this is E2, so E1 is greater than E2, because here the distance is less, here the distance is more. And generally, and so the electric field, it can be of two types. Remember, electric field can be uniform and non-uniform. So the generally we say that we can get a uniform electric field or a non-uniform electric field. Generally an uniform electric field is represented by parallel equidistant straight lines, which indicate that the magnitude and the direction of the electric field remains constant at all the points. So the distance, as the distance is equal, that means the magnitude remains the same, and as all the lines are directed in the same direction, so the direction also remains constant. So this represents an uniform electric field. Similarly, a non-uniform field can be represented by the following ways. So in this case, so the magnitude varies. So in this case the magnitude varies, because as the distance between the lines of force is changing, so the magnitude changes but the direction remains same. This is also a non-uniform field. Now in another case, suppose the magnitude remains constant but the direction varies. So this is also, here the magnitude remains constant because I am drawing parallel lines but the direction is changing. So this is non-uniform. And in another case, both the magnitude and the direction if changes, and this is also represent a non-uniform field. So in first case, this is a non-uniform field due to the change in magnitude. This is a non-uniform field due to the change in direction. And in third case, this is a non-uniform change due to the change in direction of, due to change in both magnitude and direction. So if we have a non-uniform field like this, if we have a non-uniform field like this, and if we are given 3 points, suppose this is point A, this is point B, and this is point C, and you are asked to arrange the order of increasing electric field at point A, B and C. So definitely the electric field will be stronger at the point A, because here the distance between the lines of force is less. So the EA will be greater than, so the much smaller distance is B, so it will be greater than EB, which will be greater than EC, because EC will be the least, because here the distance between the lines of force is more. So the distance between the lines of force, it represents the strength of the electric field. Now another point is the number of lines of force emerging or ending, that means beginning or terminating on a charge, it also represents the magnitude of the charge. That means suppose if we have two charges, both are positive, or one is positive and one is negative. Suppose we are drawing the lines of force like this. You can see that here 3 number of lines of force are terminating on the negative charge, but here, sorry, let us eliminate this, 6 number of lines of force are emerging from this positive charge. The 3, here it is 6 and here it is 3. So as I told you that the number of lines of force either emerging or terminating on a charge is proportional to the magnitude of the charge. So here definitely this charge, if this is Q or if this is Q, this must be 2Q, because here it has 3 lines of force terminating on it, but here it has 6 lines of force emerging from it. So definitely the magnitude of this charge must be twice in comparison to this charge. That is why it is giving rise to the double number of lines of force in comparison to this charge. So the amount of lines of force originating or terminating from a charge is proportional to the strength of the charge. So as I told you previously that the electric lines of force, they originate and terminate on charges or on conductors perpendicularly. That means the electric lines of force are always perpendicular to the surface of a conductor, because you see the reason for this is, let us explain it. If we have a conductor, then we have many number of free electrons inside it, but at a neutral condition or at normal state, the conductor does not carry electric current. That means there is no flow of electric current inside the conductor when it is lying freely. But you see, so I told you that the electric field will be perpendicular to the surface of conductor at every point or on a charged body. So if suppose if the electric field will not be perpendicular, suppose this is not perpendicular and it is at a certain angle theta, then it will have a component. Suppose this will be E cos theta. So it will have a component along the surface of the conductor. Then due to this component, the charged particle, whatever charged particle will be there, if Q amount of charge is there inside the conductor, so this Q will experience a force due to the component of this electric field, and the force will be equal to, that force will be equal to QE, because we know that E is equal to F by Q. So the force experienced by a charged particle in an electric field will be F is equal to QE. So that will, here it will be Q E cos theta. So due to the component E cos theta, this charged particle will experience a force, and under the influence of that force, the charges will come into motion and they will constitute an electric current. But this is quite contradictory, because in free condition generally a wire does not carry electric current. So the electric field must be perpendicular to the surface of the conductor, so that the component of the electric field towards the surface will be always 0. So this is the reason why the electric field intensity is always perpendicular to the surface of a conductor. So let us draw some examples showing the electric lines of force in different conditions. So if we have a positively charged sheet, thin sheet of positive charge, then if we will draw the electric lines of force this, so the same principle is applied to all the cases, that you imagine a unit positive charge and see in which direction it will move or it will tend to move. So if you will place a positive charge anywhere around it, so it will move perpendicularly away. So this will be the direction of lines of force. In this direction also it will be like this. So this is a case. Now coming to the second case. Suppose we have a positive charge here. Isolated positive charge was here. Then the lines of force would have been radially outwards. But you bring a piece of metal near it. Now how the electric lines of force will now be arranged? You will see that, because as you will place the metallic piece near this positive charge, so by virtue of induction or attraction repulsion, the positive charges will come to this side and the negative charges will become to this side. So now on the lines of force there will be attraction between the positive and negative, so the lines of force will be pulled towards the surface of this metallic sheet. So now it will be arranged like this. So it will be now like this. So this will be the arrangement of the lines of force. Now coming to the third case. Suppose we are having a positive and a negative charge. Simply a positive charge plate and a negatively charged plate. This generally happens in case of a parallel plate capacitor. So in this case the lines of force will be from positive to negative. So this will be simply represented by this. Now in this there is another exception to this case also. Suppose in this similar case we'll place a spherical ball, conducting spherical ball in between these two plates. Suppose this is positive and this is a negative plate. So first let us place another conducting thin sheet. So what will happen? This will go like this. As this is a metallic piece, so the negative charges will be attracted to this side and the positive charges will be attracted to this side. As it is placed in between two positive and negative plates, so the charges inside this plate will now be rearranged, and the negative charges will come to this side due to attraction and the positive charges will come to this side due to attraction. So there will be developed another field inside this metallic plate, and the direction will be exactly opposite to the external field, because from positive the field will be from positive to negative. So inside the plate the field will be exactly opposite to that of the outside. That is why inside this the field will be equal to 0, but outside there will be one field which will be from positive to negative. So this is the case. Now let us draw another example. In between these two plates, suppose we introduce a spherical ball or conducting spherical ball, then what will happen? It must be perpendicular. That is why I am drawing like this. And inside it the field will be again 0, and no lines of force will pass through the sphere. That is why here also same the case, the no lines of force will pass through the conducting body, which will represent there will be no field inside the conductor. So these are few cases of representing the lines of force. So now let us discuss the electric dipole. So as the name suggests, it is a dipole. That means it is having a two polarity. That means there must be a positive and a negative charge. So the electric dipole, it refers to two equal and opposite charges separated by a small distance or finite distance. So two equal and opposite charges, suppose this is plus q and there is minus q. These are two equal and opposite charges. They are separated by a finite distance. Suppose let the distance be 2a. Then this arrangement is called as an electric dipole. So an electric dipole consists of two equal and opposite charges separated by a finite distance or small distance, you can say. So now coming to the dipole moment. So the dipole moment is a vector quantity. Remember, it's a vector quantity whose magnitude, it is symbolized by the vector p, and its magnitude is given by the product of magnitude of either of the charges, as both the charges are equal. So it is the product of magnitude of either of the charges to the perpendicular distance between them. So here the distance is 2a. So the magnitude of the dipole moment is 2qa. So this is the magnitude, and the direction is from negative to positive charge. Remember, the direction of the dipole moment is always from negative to positive charge. But as we saw that when there is a positive and negative charge, the electric field will be always directed from positive to negative. Definitely, because in order to calculate the direction of electric field, we generally place a unit positive charge and see in which direction it is moving. So if you consider a test charge, then the test charge will be repelled by the positive charge and attracted by the negative charge. So it will move from positive to negative. So the direction of electric field is from positive to negative, but the direction of the dipole moment is from negative to positive charge. That is why we always say that the dipole moment always opposes the strength of electric field, because the electric field is from positive to negative, whereas the dipole moment is from negative to positive. That is why the dipole moment always opposes the strength of electric field. So its unit will be definitely its charge into distance, so it will be coulomb into meter. The SI unit will be coulomb into meter, otherwise called as the dBi. In nature, we generally see the dipoles like water, where we have oxygen, more electronegative element, and the hydrogen, two hydrogen atoms, which is bent in the form of B or bent shaped, where oxygen is more electronegative and hydrogen is more electropositive. So the direction is from more electronegative to more electropositive element, or the towards the direction of the dipole moment is from negative to positive. So that is why it will be towards this. It will be from negative to positive. So the direction of the dipole moment will be towards this. Similarly, in case of hydrogen fluoride also, HF, the fluorine is more electronegative. So this is also one example of an electric dipole. Now, one term is frequently used in case of electric dipole, that is one ideal electric dipole. You can say the ideal electric dipole, or an electric dipole is said to be ideal. We generally say that two equal and opposite charges separated by a small distance or finite distance is called as an electric dipole. Then what is an ideal electric dipole? So an electric dipole will be an ideal electric dipole, or will be called as an ideal electric dipole when the magnitude of each charge, suppose we are having a plus q and minus q charge separated by a distance 2a, then if the magnitude of the charge increases to infinite or tend to become infinite and the distance between them reduces to 0, that means here the 2a tends to become 0, then this dipole will be called as an ideal electric dipole. So an electric dipole is said to be ideal when the magnitude of each charge increases to infinite and the distance between them reduces to 0. Under that condition, an electric dipole will be called as an ideal electric dipole. See, so if we are having a dipole, each having charges plus q and minus q separated by a distance 2a, then the line joining the two opposite charges of the dipole is called as the axial line, or otherwise called as the axis of the dipole. It is called as the axial line. So this line which is joining the two opposite charges, the straight line joining the two opposite charges of the electric dipole, is called as the axial line. And the line which is passing through the midpoint of this axial line and is perpendicular to this axial line is called as the equatorial line. So the line which joins the two opposite charges of the electric dipole is called as axial line, and the line which passes through the midpoint of this axial line and is perpendicular to the axial line is called as the equatorial line.